Justin Miller, welcome back. Oxnard College Physics. Yeah, we're gonna look at another problem here involving net force due to multiple forces acting. So this one's just kind of a little exposure to what happens when you do have multiple forces acting. How do you go through it all so we work out a problem having it? So here's the problem. All right, so what do we got? We've got ourselves a mass of 2.5 kilograms that is subject to 3 different forces simultaneously acting on the object. So let's draw out a little picture of what the words we're saying here. So let's draw out what is known as a force diagram, where ultimately we just have a depiction of an object with the forces acting on it in the directions that they're acting on. So we'll take our mass M here and note that M is equal to 2.50 kilograms. And then we're going to draw some forces in here. We'll do some purple forces. And we're going to say that force number 1 is 10 newtons at 35 degrees. So we'll say 35 degrees, maybe something like that. F1 hat is equal to 10 newtons at 35 degrees with respect to the horizontal. And we can take another force and say we've got an F2 that is 12 newtons at 155. So 180, 25, we'll say 155, something like this. F2 hat is equal to 12 newtons at 155 degrees. We'll take one more force and say that it's 8 newtons acting at negative 75 degrees. So negative 75 degrees, we'll say something about like this. That's a little too long. 8 newtons. We've got ourselves an F3 hat is equal to 8 newtons at negative 75 degrees. And our question is, what is the net force? First, as just unit vector notation. So A, we want to write sigma F hat is equal to sigma F sub X I hat plus sigma F sub Y J hat. That's what we want to write. So in order to write that, we need to know what is sigma F sub X and what is sigma F sub Y. Let's just go ahead and state out what those would be looking like. Sigma F sub X would be the sum of all the X components of these 3 forces. So we'd have that is F1X plus F2X plus F3X, where sigma F sub Y would be F1Y plus F2Y plus F3Y. So then it comes into B, what are those F1, 2, and 3's X and Y's? So that all is a matter of resolving each of these vectors into its X and Y components. So let's just do X components, Y components, then we can add them all up. So do a little presto changeo color-wise. And we will do this. We've got F1X is going to be equal to the magnitude of F1 multiplied by the cosine of a theta 1, right? That's how we get magnitudes, that's how we get components. And we'll say that that is then 10 newtons times the cosine of 35 degrees. F2X is going to be equal to a magnitude of F2, which is 12 newtons times the cosine of 155 degrees. And F3X is going to be equal to the magnitude of F3, 8 newtons times the cosine of negative 75 degrees. And that's something we can now stick in our calculator. Back to the old one, that's okay. 10 cosine 35, 12 cosine 55, 8 cosine negative 75. And get some nice values here. 9.1915 9.1915 newtons. We get a negative 10.876, negative 10.876 newtons, and then a 2.0706. 2.0706 newtons. So notice signs with things, right? Let's just make sure we've got the right sort of sign correlation here. F1 should have a positive x component. F2 should have a negative x component. And F3 should have, well, positive x component. So positive, negative, positive, those seem to make sense, correlate well. Let's go on over to the y's, right? So we've got the F1y is going to be equal to the magnitude of F1, again, which is 10 newtons, multiplied by the cosine of 35 degrees. F2y is equal to 12 newtons. Nope, sorry. Cosine, sine. These are the cosines. Sine of 35 degrees. F2y is 12 newtons times the sine of 155 degrees. And F3y is equal to 8 newtons times the sine of negative 75 degrees. So ask this, which one of these, or which ones of these, should be negative? Which one of these forces, which ones of these forces have a negative y component? Does F1? No, there's a positive y component. Does F2? No, it's got a positive y component. Does F3? Yes, it has a negative y component. So we should get that this one ends up being negative. Well, let's go ahead and compute all these and see if that is indeed the case. 10 sine 35, 12 sine 55, and 8 sine of negative 75. And the values that I receive here are 5.736, 5.73, say 5.8 newtons, 5.0714, 5.0714 newtons, and this one does come out to be negative 7.27, 7.7274 newtons. So there we've got all the individual x components, all the individual y components. What do we get? Sigma f sub x is just the sum of all those. So we've got 9.1915 plus negative 10.876, negative 10.876 plus 2.0706, 2.0706 gives us 0.3861. Really should only keep it out to that. That's okay. We'll just keep it like that. Newtons. Come over to these, and we've got ourselves 5.7358. 7358 plus 5.0714, 5.0714. Minus, we'll just say, minus 7.7274. 7.7274. For this, we've got ourselves sigma f sub y is equal to 3.0798. 3.0798 newtons. So in the end, for part A, we can write ourselves sigma f hat in unit vector notation is equal to 0.3861 newtons I hat plus 3.0798 newtons J hat. If we wanted to round those out to three significant figures, that would be perfectly fine, but this would be what we've got going on. So ultimately, we've got a little x component and, well, a y component that's about 10 times as big. Not quite 10, 9 something. But most of the net force is pointing in the positive j hat direction, a little bit in the x. Well, let's see what that really looks like. How are we going to see what that really looks like? Let's get part B, magnitude and direction. B, we want the magnitude of the net force. Well, that is going to be the sum square root, excuse me, of the sum of the squares of the x and y components, which is then equal to the square root of 0.3861 newtons quantity squared plus 3.0798 newtons quantity squared, which gives us the magnitude of the net force being equal to 0.3861 squared plus 3.0798 squared. This is good. 3.1039. 3.1039 newtons. The overall net force, a little bit over 3 newtons. What is the direction of this net force? Well, given that we have a little x component that's positive and a significantly larger y component that's positive, what do you think that means? Little x, a lot of y, both positive, should definitely have a vector that's pointing into the first quadrant, right? And because the y component is much bigger than the x component, it should be on the high side, nearing 90 degrees. Is it exactly 90? No, maybe 80 something, maybe high 70s. I don't know, we gotta compute it out, right? Theta sigma f is gotten by looking at the arctangent of sigma f sub y over sigma f sub x, which is then the arctangent of 3.0798 divided by 0.3861, which is equal to arctangent 3.0798. 3816. 861. Oof. Sure, I'm putting those in right. All right. 82.854. 82.854 degrees. So in terms of the magnitude and direction, we could write that sigma f hat is equal to 3.1039 newtons, or we could just say 3.103 significant figures, at an angle of 82.854 degrees with respect to the positive x direction. There we go, magnitude and direction. What does that look like? We can come back up to our graph, right? And say, well, this is scaled to be 8. 3 would be about like this, but instead of pointing in this direction, it's pointing up at like 82 degrees. There's our sigma f hat right there. The overall net force due to these 3 forces acting is this. This is what ultimately results. Something pulls that way, something pulls that way, something pulls that way. With those particular magnitudes and directions, the net outcome is an overall something pulling that way with pretty small magnitude compared to the individuals and a pretty steep angle at that. Way different angle than any of them. So what's the point with this? Have to be able to break things down to x and y components. We couldn't just add, oh, the net's going to be 12 plus 10 plus 8. That's going to be 20 newtons. We kind of add up the angles and say, oh, 20 newtons at this degrees. Doesn't work like that. Vector algebra. Make sure you got it down. It becomes highly important. So last one more thing, 2 more things. Part C. Assuming that these 3 forces are acting simultaneously, what is the overall acceleration of this object? Once we've got the net force, we know that the net force produces the acceleration of the mass. Furthermore, we know that the magnitude of the net force is equal to the mass times the magnitude of the acceleration. Why can we say that? Well, because their directions have to be the same. We've got that theta sub sigma f has to be equal to theta sub a, which is our 82.854 degrees. Same direction, we've got to have that they have a proportional magnitudes then. Constant of proportionality is the mass, thus we've got that. The magnitude of the acceleration can be written as the magnitude of the net force divided by the mass, which is our 3.1039 newtons, divided by the mass of 2.50 kilograms, which 3.1039 divided by 0.25, divided by 2.5, gives us 1.242, we'll just call it 1.242 meters per second squared at that angle there. That's it. There's the acceleration that's produced overall. What if we said, what is the velocity of this mass? What's the velocity of this mass? If it starts from rest and we let it move 15 meters from where it initially was. So D is V final equal to, if V initial is equal to 0 when these forces acting on it, when these forces start acting on it, and it has moved by 15 meters. Well, this we've got to be a little bit careful with because, well, if it's moving by 15 meters, what direction is it moving in if it's initially at rest? Well, that's a good question, right? So we've got this object here, like this. We've got this net force. Now we don't really care about the individual forces. We've already got the net force computed. We've got this being equal to the net force, which produces that acceleration there. And we have that this object is initially at rest. So if something's initially at rest, then something pushes on it that way. Which way is it going to move? That's right. It's going to move in the direction of whatever's pushing on it. Now, if it's already moving, it would have some motion that starts to get coupled in with the force. We're not worried about that. This object's initially at rest. Initially at rest, the net force acts on it. It's moving in the direction of the net force. That's the direction of the acceleration. That will always be the direction of the motion then. So this object here is going to do this. It is going to move 15 meters. Well, that 15 meters is in the direction of the net force. Let's call that direction delta R hat. It's a displacement. And what direction? In that direction at 82.854 degrees. Is this one-dimensional motion? You say no, because it has both X components and Y components, which is definitely true. It does. But it's straight line motion. Neither are changing with respect to time in terms of the direction that it's moving. If it's always moving in the same direction, that's really one-dimensional motion. But we can't call it delta X or delta Y here. We can do this. Always moving at 82.854 degrees, since the initial is equal to 0 and the force is constant here, as long as those three forces continue to act in those orientations throughout time. This is one-dimensional motion, and we can write things like this. Delta R is equal to 1/2 a t squared plus vi times t. We can write that v final is equal to at plus v initial. And we can also write that v final squared is equal to v initial squared plus 2a delta r. What do? We just generalize the equations of motion for constant acceleration into the delta r hat direction, which we could resolve into a delta x hat plus a delta y hat, but it's unnecessary. We just want to know how fast is it going? Well, that's this v final here. It has both x and y components. I don't care. Overall, we just want its speed. So this would be the nice one to use. We know how far it moves, we know what its acceleration is, and we know that it's initially at rest. So with that, we've got ourselves v initial is equal to 0. We want a v final. We've got an acceleration that is our 1.242 meters per second squared. And we've got our delta R, which we're saying is 15 meters. So how fast is it going? let's just go ahead and use that other one over there. We've got a V final squared is equal to V initial squared plus 2A delta R, giving us that V final is equal to the square root of 0 plus 2 times 1.424 meters per second squared, multiplied by 15 meters, which gives us that V final is equal to the square root of 30 times 1.424. This gives us 6.536. 6.536 meters per second at that 82.28 something, 82.854, 82.854 degrees. And again, this is because it started at rest, so it's always moving in that direction. And so put that back down. See what we've got. That was a good problem. Problem involving vector force, or vector forces, adding them all up. Get used to it. There's a lot more of this to come. Have a good one.